Hello everyone, I'm Jorge González and I'm going to explain my thesis titled Design, Manufacturing and Testing of a Fly Actuate UUR Wind Energy Demonstrator under the supervision of Gonzalo Sánchez Arriaga from the Aerospace Engineering Department and David Santos Martin from the Electrical Engineering Department. As Paco was explaining before in the previous presentation, wind energy is an important topic nowadays in the energy generation. There are several companies and universities that are involved in this development. A few years back, UC3M and FET Ingenieros had developed a new ground station that we can see before that is compatible with the 3 lines and 1 line system. So these test beds can be used to explore new direction related to wind energy, like the onboard control that I want to develop. So another important thing of the motivation is that there are many examples of wind energy system and test beds that use external pod or control surfaces, but no one has attempted to integrate the control mechanism into the kite. So let me explain something about the scope of the thesis. I have 2 branches on the thesis. The first one is to complete the development and to define the development of the electrical subsystem of the ground station that we see before. And the other branch is the design of this new onboard actuator system, this new system, and integrate into the kite that you can see in the picture. So in the first branch, I was involved in the support of the design of the electrical system topology because this application of the wind system is really strange because we have very variable forces in the tethers, and it's not very easy for the battery to get this current, and also it's not very good for the lifetime of the battery. So that's why we include the supercapacitors to get this peak of the current and minimize the damage that we can cause to the battery. The second test that I was involved was in the definition of the communication architecture for the energy management system. So as Paco was showing in the previous slide, there is a PLC that is like the master controller and also manages the safety of the system, of the electrical system. And it's important this communication and strategy to operate in real time and see what is the current in each point, what is the voltage, and how to operate in case you have an overcurrent or an overvoltage in the system. So the third one is the development of that is ongoing, is the development of the real-time hardware in the loop kite emulator for testing the electrical system, because it's very difficult to perform flight tests. We depend of the wind speed, we depend of everything. If we want to fly, we cannot say, okay, tomorrow we are going to fly. So it's better to have a hardware in the loop emulator. And now we are working on this, that we can see in this here, where one machine is operating as a kite emulator, performing the torque, and the other one is operating like the real generator that we have in the ground station. And finally, I also collaborate in the design of the experiments to validate the electrical system. Okay, the other branch of my thesis, I'm going to explain a brief explanation about the state of the art. Okay, we can see ground actuates ground station. Okay, like the one that I was explaining before, and also NRK has another ground station, where we control the kite for moving the tether from the ground station. Okay, so there are some limitations of this system. One of them is that the drag forces of the tethers are greater because we are using 3 lines instead of 1 line. Another limitation is that the length of the tether is increasing. The control issues may arise due to physical delay, because if we have 300 meters and we want to perform an action from the ground station, there is a delay between the action that we do and the kite receive this action, right? And the second group is the onboard actuator system, the fly actuator system. And we can find control surfaces, like we can see here, like traditional aircrafts. And this is from Antis Power, a company. But of course, we can find some limitation. We add weight to the aircraft due to the actuators for the control surfaces. Also, we have, this solution is limited just to the fixed wing aircraft. It was possible to adapt to the flexible or semi-rigid kites. And also it has a high manufacturing cost. So also we can find another system that is using this external pole. Okay, but the problem is, okay, we have here the system that modified the length of the line, but we are way out far from the center of the mass of the kite, so it's not very good for the maneuvers. And also we are increasing the drag due to the pole. So that's why we define some goals of my thesis. One of them is the design of the system, but also the manufacturing and testing of the prototype. And also one requirement is that the system must be compatible with integration with the ground station that we have now. Okay, and we can set some advantages. One of them is now the delay does not occur due to the cable length because the actuator is on board. Okay, the length of the line is not too much to modify. So the drag caused by the pod now is eliminated because it's not here. It's integrated into the kite, and we can modify the shape of the kite to optimize this drag. And we use just a single line, so the drag for the line is reduced. And also it's not limited to the fixed wing kite. We can adapt to a flexible kite or a semi-rigid kite. So here we can see the first prototype. Okay, in the middle we can see the kite control unit. That is the system that modified this belt to modify the length of the lines and different anchor points. And here I'm going to explain a little bit about this kite control unit. Okay. We send the data. Okay, we have different systems here. We have a lithium battery to power all of the microcontroller, the energy control system that send the command to the actuator, and we have an encoder to read the position. And we send the data from the ground station, the reference value that we want, the delta of the line that we want. We receive the data on the microcontroller, and here we send using canvas communication to the energy control system. It sends some electrical signals right to the actuator, and the actuator starts moving, and we read the position from the encoder. Okay. Here we can see the real picture. With this system, I implement an open loop. It's different from the closed loop that Paco was doing before. This is a very simple model. We have a joystick, and we can control from the joystick, from the ground station, we can control the delta line of the line of the kite. Okay, so we can figure out by just operating with our operator modifying the joystick, and we can perform the maneuver. This is an initial approach. Okay, I want to work in a closed loop PID controller after this initial model. Okay, my control variable is this delta line, that is the difference between the line LA and LB that we can see here. And we read the voltage from the joystick. We have an analog to digital converter, some digital filter, secondary digital filter to smooth the signal. And this is a gain value to convert the voltage to the maximum angular position that we want. And here we can see an inner position loop, where it's performing this ESD controller. And after that, we have the real position, and this is the mechanical part that converts this angular position to the final delta line. With this system, I did some simulations that give us good feedback about the design parameters. Okay, now we know that we are in the correct direction. We can see that the forces over the actuator are okay with the requirements of the actuator. We can see that the delta line that we perform is enough to perform this maneuver. And we check that all of the forces and the speed that we need in the actuator are below the limits. And also we perform some flight tests, and we check that the communication link between the ground station and the actuator was okay. We can operate at some hundred of meters and move the joystick, and everything is okay. The delta line that we set with the joystick is the real delta line that we measure in the actuator. And we were always able to maintain the kite in the right position. But the problem is that in the flight test, we have some issues with the structure of the kite. And we get a lesson learned that indicate the needs to reinforce the critical structural points. Okay, because as you can see here there is a carbon fiber bar. We need to reinforce this part because we have some damage in this section. Okay, and finally some journal papers about this, about my thesis. Conference, I forgot here to put the conference that we have this month in Nantes in France, and some dissemination activities in the Spanish TV channels, and also Semana de la Ciencia, and some events to disseminate the information about the urban wind energy system. So that's all from my side. Thank you for your attention.